Okay, we're going to prove that C is a field. So what does it mean to be a field? Well, the addition that we defined previously needs to be associative, commutative, needs to have identity, needs to be, well, it doesn't quite make sense what I wrote, but that's okay. Needs to have identity, and needs to have additive inverses. I'm just going to write inverses. All right, so let's see. Associativity, let's start there. I can't spell, it looks like. Let's try again. There we go. All right, so let's take three complex numbers, a1 plus b2i, a2 plus b2i, a3 plus b3i. So these are three complex numbers. And we need to check that if we add a1 plus b1i and a2 plus b2i first, and then add a3 plus b3i, that needs to be equal to the same, but with the parentheses swap. So I'm not going to write that out. We're going to do this computation, and then I'll swap the parentheses for the next one. All right, so we have to work inside the parentheses first. So we have a1 plus a2 plus b1 plus b2. Why is that? Well, that's just applying the definition of addition. And now we add this complex number that has a real part a1 plus a2 and imaginary part b1 plus b2 to the complex number with real part a3 and imaginary part b3. And the rule is, of course, just to add the real parts and the imaginary parts. Now, addition of real numbers is associative, and these are just real numbers, right? The real and imaginary part are just real numbers. And so it doesn't really matter where we put the parentheses here. So one could even write just a1 plus a2 plus a3, because it does not matter the order in which you add them, and b1 plus b2 plus b3. So one could write that, and I will. All right, so this is, let's call this star for a second. We have to check that star is the same as adding a1 plus b1, put the parentheses wrong spot, a1 plus b1i, plus the sum of a2 plus b2i and a3 plus b3i. So we leave the a1 plus b1i alone, and again, we add inside the parentheses first. And then we add real and imaginary parts. Oops, it's one too many parentheses here. Just start over. a1 plus a2 plus a3. And then the imaginary part of the first one's b1, and then the second complex number is b2 plus b3. And of course, it doesn't really matter the order because this is addition of real numbers, and real numbers are a field, so it's associative. And so we, of course, get that that's also star. And so this means that addition is associative because it doesn't matter how you associate, you get the same answer. Okay, so that was kind of long, and in the effort of keeping this proof under 10 minutes, I'm not going to prove that multiplication is associative when we get there. Now let's check commutative. This will be much faster. Throughout A1, the A's and the B's will be complex numbers as stated in number 1. So we need to check that A1 plus B1i plus A2 plus B2i is the same as A2 plus B2i plus A1 plus B1i. Let me phrase this as a question. Okay, it's a question now. All right, on the left-hand side, the rule for addition says add the real and imaginary parts. So we do that. We do the same thing on the right-hand side. But this is addition of real numbers, and so the order of addition doesn't matter. So are they the same? Yes. Put a gold check mark. Put a gold check mark to indicate we're done. Great. It's commutative. We need to check identity. And the identity is going to be 0 plus 0i, which we normally just write as 0. It means the same thing. But let's keep it as 0 plus 0i for the moment. What does it mean to be the identity? Well, if we add a1 plus b1i to 0, we should get the same thing back. So a1 plus 0, and then b1 plus 0 is the rule. So that's, again, a1 plus b1, because 0 is the additive identity for real numbers. And of course, the same is true the other way, because addition we just saw was commutative. So we get the same answer the other way. So this is, in fact, the identity. We need additive inverses. So if I take a1 plus b1i, what should the additive inverse be? Well, it should be negative a1 plus negative b1i. And if we add the, oh shoot, I forgot my gold check mark. If we add these together, we get a1 plus negative a1, b1 plus negative b1i, and that's of course 0 plus 0i. So additive inverses exist. Okay, so it behaves, it satisfies all the 4 checks for addition. And now we have to check the same for multiplication, almost. Namely, when we do multiplicative inverses, it's not for all elements, it's just for non-zero elements. Okay, so that's what the almost means. All right, associativity. Long and tedious, but not hard. Let me explain. You have to replace the symbol plus with a times and plus with a times and do the multiplications according to the parentheses, and you'll see you get the same thing. I'm not going to do that. Commutativity I will do. So a1 plus b1i times a2 plus b2i, we have to ask, is that the same as a2 plus b2i times a1 plus b1i? Let's put a question mark to indicate we don't know. The rule is multiply the real parts, subtract the product of the imaginary parts, and then the cross terms are, the sum of the cross terms is the new imaginary part. Multiply the real parts, subtract the product of the imaginary parts, and then the cross terms are the new imaginary part. These ones match. Let's see, let's use green. These ones match on the nose, and these ones match because multiplication of real numbers is commutative, so you can switch the order of multiplication for both of those terms, and you get that term. So is this true? Yep, it gets our gold check mark. We need identity now. Well, it's going to be 1 plus, I don't need parentheses, 1 plus 0i, which we're just going to write off as 1. And if you take an a1 plus b1i and you multiply it with 1 plus 0i, what you're going to get is product of the real parts minus product of the imaginary parts, plus the cross terms are the new imaginary part. That goes away. That goes away. And we get a1 plus b1i as desired. Now multiplicative inverses of non-zero elements. So given, let me just say inverses. Let me scroll up a little bit. I don't think I'm going to make this under 10 minutes. Oops. Let's suppose a1 plus bi is not equal to 0 plus 0i. That means both a1 or b1, it cannot be that both a1 and b1 are 0. And so what we're going to do is we're going to notice something. Let's notice that, and this will be something that's an important observation for later examples. If we take a1 plus b1i and we multiply it with the conjugate expression, this this guy, if you multiply it out, you get a1 squared plus b1 squared. This is sometimes called the modulus squared. We won't need that for right now. But the point is that since a1, b1 are not both 0, the right-hand side, this guy here, is not 0. In particular, since it's not 0, we can divide by it. So we get a1 plus b1i times, let's divide by a1 squared plus b1 squared, and we're only going to divide this guy by it. And if we divide both sides by that on the right-hand side, we're going to get a 1. So what we've learned here is that a1 plus b1i inverse is a1 over a1 squared plus b1 squared. And then I have to divide also the imaginary part. And that's a formula that we can always apply for the inverse of a complex number. And later, actually, we'll use this formula in other subsets of C to find an inverse. But this is a helpful tool. We took our complex number and we multiplied it with the conjugate expression. Later on, we're going to see there's more than one conjugate expression in general. But we multiply it with it, and then that creates a real number, or something that we know how to compute the inverse of. We just do 1 over it, and then we leverage that. All right, the last check is the distributive property, which is the linking of multiplication and addition. So we have to take a1 plus b1i and a2 plus b2i plus a3 plus b3i, and we have to show that that's the same as distributing. So let's compute this one first. So again, we're not allowed to use the distributive property to prove the distributive property, so we have to carry out the operations as they appear. So that's doing the sum inside the parentheses, and now we multiply because we have a complex number and then just a single complex number. So we get product of the real part minus product of the imaginary parts plus the cross terms. So the real part is a1 and the imaginary part's b2 plus b3. And then b1, a2 plus a3. And that's the new imaginary part. Whew. All right, so let's call that star. And now we have to compare that with multiplying a1 plus b1i with a2 plus b2i and a1 plus b1i with a3 plus b3i. Okay? We want to show that it's the same as that. So we have two products to do here. We have a1, a2, product of the real parts minus product of the imaginary parts plus cross terms times I. I've been putting this in the other order, but it doesn't matter because it's multiplication of real numbers. And then similarly for this second guy here. So this is the first one. And then we're going to do that second one now. So that's a1, a3 minus b1, b3. Let's see, plus cross terms. So that's a1, b3 plus b1, a3, and that's I. All right, and that's that guy. All right, let me just go through with a red check mark, and let's go and cancel them. So we have an a1, a2 here, a1, a2 there. We have a b1, b2 here, b1, b2 there. We have a a1, b2i down here. And then here is going to be an a1, b2i. And then we have a b1, a2i. Here's going to be our b1, a2i here. Oops, got rid of the 1 somehow. All right. And then we have an a1, a3. Okay, that's going to be distributed there. We can cancel that. And we have a negative b1, b3. All right, those match up there. And then we have an a1, b3i. Okay, a1, b3. All right, that's there. And then lastly, b1, a3. Okay, they all match up. And so it's distributive. So C is, well, distributive property holds. Distributive law holds. And that's all the checks we needed to do, minus me cheating for associativity and multiplication. So C is a field. Fantastic.